Hey guys, how's everything going? This is JSer. So in this video, I'm going to solve another problem from LeetCode, not BFE this time. It's been a long time since my last submission on LeetCode. Okay, it's 1584, mean cost to connect all points. So we are given an array points representing integer coordinates of some points on a 2D plane. Okay, this is x, y. The cost of connecting two points, the Manhattan distance between them. So it's not the length of the direct link, right? It's the Manhattan distance, which is the sum of the distance between the coordinates both horizontally and vertically. We need to return the minimum cost to make all points connected, and all points are connected if there's exactly one simple path between two points. There's no extra points, right? No extra edges collecting two points. Okay, I understand this, and sorry, I cannot solve this by myself. Well, I don't know where to start actually. So I searched on the internet, and it actually has a special algorithms for this kind of problem called minimum spanning tree. So this is a Kruskal algorithm. It's on Wikipedia. I hope you can search for it. It's well documented, and there's a graph explaining it. So here I'm going to do a brief explanation and a brief proof for it. Okay, so the basic idea is very simple. So we just to collect all points, we actually, the goal of our problem is to choose a subset of the whole edges, right? There will be like the edges here, there's a C, N2, a 2 out of N kind of the combination, right? So 2 out of N ways of the edges. These kind of edges, this is the whole edges. We just need to pick by ordering them first, sorting them first. Like smallest one is 5 here. So we choose any of them. They are both not generating circles, so we choose them. And then 7 is the smallest, we choose them. And then 7 is the smallest, choose them. And next smallest one is 8. Each will generate a circle, so we give them up. And 9, give them up. And this line, which are not generating circles, we choose them. So now all the points are connected, right? We can track the selected points by using a set. It's very simple, and detecting the circle is also very simple. We just to see if both of the points are already in the set, and yeah, we can solve it. So the proof, how to prove that this is the minimum spanning tree is a little trick here. So it's actually written down here. It's very interesting. So I'll try to explain here with my own words, right? Okay. So suppose we were doing Kruskal's algorithm, we get the tree like F, and actually the minimum MST, we called it T. Okay, this is the MST. We need to prove that F is T, right? So as for the initial case, F will be empty, and it will gradually have more elements like edge 1, edge 2, edge m, right? So we will do this like iteratively, prove this iteratively. Suppose we already proved that E1 to EK is already subset of T. How could we prove that EK plus 1 is also in T, right? If you can prove this, it means that F is the same as T. Okay, we can do this by first suppose that it's not there. EK1 is not if. Suppose it's not in T. What happened in T? Then if it is not in T, then T plus EK plus 1. We add this edge to this best, like the minimum spanning tree, then each will create a circles, right? If it is spanning tree, all the dots are connected. If we add one new edge, it will create a circle. This will create a circle, right? And since we already created a circle, there will be at least 2 more edges, right? So this will at least two more edges collecting in this circle. Since in F we avoided circles, right? We avoided circles, so this ek plus 1 in F would not create a circle, right? And in two more edges so these two more edges, at least one of them, let's say how can I say, if x, okay, ex, ex, at least one of them, ex, is not in F. Why? Because this ek1 is chosen in by our logic in generating this F, right? They will not create circles. So at least one of them is not F. It is, if all of them are in F, then it will generate a circle in F. So it's not in F, right? And because we already chose this ek1 in F, it means the ex is bigger than at least equal e to e. What do you say? Ek plus 1, because we are choosing the node edge in the sorted order. So this was before ex, right? If we put this ex in our wait a minute. So if ex is smaller than it, if ex is smaller than ek plus 1, it will be chosen in our F first, before, right? Because you are connecting dots here. So it must be ek smaller than ex, at least this edge, right? If this x is smaller, then ex will be chosen before ek plus 1, right? Sounds reasonable? Yeah, and then we could say, you see, if we you see, this is smaller than it, and yeah, so you see, we smaller than it, and t, if we replace this k plus 1, right? If we replace this k plus 1, we replace this ex with ek plus 1, right? So I mean, if we replace ek plus 1 to okay, no, ex, this ex is in t, replace it to ek plus 1, what will happen? It will actually create smaller spanning tree, right? So t, our first assumption is that t is the minimum spanning tree. Now this is the paradox. So this is not true. This is not right. So ek1 is also in t. So we prove. Okay. So f is the LMST, which is the t. So we prove that. So now we can write the code as we analyzed here. We use we sort the edges, and then we use a set to keep track of the point. And what we need to return, we need to return the minimum cost. Okay, so first we need to create a sort the edges. Okay, so the edges, we just create empty here. How should I? Okay, the edge actually consists of 3 elements. One is the from, and then to, and then this is the weight. Okay, the distance. Okay, cool. So we do it. So for I points, let j equals j plus 1, j. Okay, this is dot length minus 1, smaller than point, sub than plus plus. So we push into the edges. Oh wow, we push it, we could sort it. That could actually generate an insertion sort. Yeah. Yeah, so we can do insertion sort, or we just pushed it in and do the quick sort. Yeah, we can do that. Okay, we just push the edges in. We push I, j, and this is the we need to get the Manhattan distance, right? Is this okay? So this should be math abs points I 0 points j 0 plus math abs points I 1 points j 1 math push. This is, wait a minute, okay, this is right. And then we sort the edges sort. We sort by the distance. This is sort by distance, and then we need to keep track of the nodes, right? So selected points. We new set, new map. Okay, map. New set. The set would be a string. A key will be a string by x, y. Okay. So now we loop through for each edge of edges. If there is a circle, skip. So if there's a circle, it means, okay, the edge actually x, y, this is the distance. If selected points, okay, it's not right. The edges actually have a from to. Yeah. Okay, this is I. No. I'm sorry. It should be I G. It's right. It's first two actually is not x y, but from to. Cool. Selected points would be if this from is in the points, or okay, we use another function. Try to create a function. Is selected. This is a point. We use point. If selected points has point join return true. Oh, okay. And just to return this is enough. Yeah, so is from selected would be is selected from, is to selected. We do the same. Is selected to. So if both are selected, then we skip, right? Continue. If not, we need to add them to the selected points. So select point push from join underline, and we push from to join underline underscore, and we need to get the result. So I'll say let result equals 0. We push it into the select points, we plus it with the distance. Cool. Return the result. Yeah, so this is actually the reflection of this Kruskal's algorithm. I hope it works. Let's review it before I submit. Edges, so each point I j, there's a typo here, I plus 1. I go to the point before the last one. Okay, j goes to the last, and then we will push these edges from 2. This is the Manhattan distance, I1 0 j0 I1 j1. Okay, and then we sort it with 1 0 1 2, the distance. Cool. And then use a set. and we loop through the edges, and if from to is all selected, both selected, we skip this point. If not, we push this from and to into the selected point and update the distance. Yeah, I think it should work. And time limit pending. Man, I've already bought the membership. Not a function. Join. Join that point from is I. Oh God. I'm stupid. I'm sorry. This is not at J. This is point I, point J. Okay. Point push is not. It's not push. It's set. So it's add. Great. Hope it works, man. Come on. Wrong answer? What? We got expected 53. We got 29. Yeah. I'm sorry. I need to break once we have the select. When we found that select points is enough, right? So yeah. So if selected point size is equal to our points.length. Shit. We break. This should work. Come on. No. Select points. Really? Okay, we get 29. Okay, allow me to log it. From to distance, and then picked. First is this one. Distance is 7 picked. 22 picked. Actually, we have 4 points. Yeah. No. I made a mistake. So points, yeah, like 5. We need to add. Like this is 4 points is chosen, but actually we need the edges. So there's a mistake. We use set. So this, like, if we choose the first one here, and then we add this one, there actually is no circle, but we treat it as a circle by simply checking if the points are in it or not. How can I check that if this generates a circle or not? If generates circle, what happens? We could do DFS to search for it. Okay, for the other case, how should we do? Like, what can we do if these two are connected? I'm sorry. I made a mistake. We cannot simply use set for this, but using use selected edges. Okay, the selecting the edges means how can I do this? I mean, we could just search for from the from, right? Search from and DFS if we can find the two. So we need actually need a map. Okay, so selected edges, which is new map. This is actually a map of a point to a set of points. Okay, so is generating a circle. This is point. We could to do later. So if generates from generating circle, new map, a point cannot, so point, okay, it's from to is generating circle from to. If it's generated circle, we do nothing, and actually this doesn't, it is not needed. Yeah. Size, okay, yeah, this is not needed. We could improve it when we find it. Okay, I'll just improve it by tracking the edge selected edge count, because this is the map from point to a set of point. We better just track it with another variable. Result plus instance, this plus 1. Okay, if selected point is our length, we break. And selected edges we need to add, right? We create another method called add edge is from to. Okay, then we implement this add edge, const add edge from to. For add edge, it's pretty simple. We say if we need to do this. We need to do this both from to and from to from, and in a reversed way. So if selected edges has from, we add a 2 to the set. Get from. Okay, the key. Key from equals from join times key 2 to join. We get key from. We get key from. Add key 2. If not, we set it. We just set key from. New set key 2. Yeah, and we will do this. We need to do the same for the 2. Or we could just store the index. Yeah, we could store the index of the point, right? If that's the case, we just from 1 to 2, and then yeah, that would be simpler. Okay, we just stick to these the string as a key, and then try to improve it. Selected tree has key. We need to do the reverse fashion. So 2, 2, 2. From. So we have a we have a full map for the edges. Now is generate circles. Well, we could just start from. If there's a circle, either way will be fine. So I'll do it. Use it in a DFS, use what? Use a stack. Okay, stack is okay. Go to stack. Oh, first, if it is not in it, then it's definitely not gonna work. Huh? If there's no nodes in this selected edges map, then definitely it's not gonna create a circle, right? So if pass from, because the key from equals from join. Oops, there's key from. If not, then we return false. If there is, we put from in it. Yeah, in it. Yeah, we could use. I like to use Q for this. Yeah, okay. Let's create another set called visited equals new set. Stack is also right. Stack. Okay, we could just use stack. While stack is not empty, we get the pop it up. Stack pop. So if it is 2, top equals 2, then we return true. If not, we will push their connected dots in it. So for if this is top, so if selected edges has top, key from it should be. If has it, then for let 2. Okay, we don't need this 2. Oh, we need to check the 2. Okay, just the from. And then we call the is generating circle from const. No. Yeah. If there is a circle, we could do this. Oh, no problem. So this is 2m. I'm sorry. So for next of selected edges, you get top. Okay. Oh, okay. We get the next if visited doesn't have it. If visited has, next we continue, right? We do nothing. And if it is not visited yet, we push it into the stack. Stack push. Okay, this is not visited yet. This is, I think, is walked. It's the same actually. Anyway, stack push next, and then we need to add this walked into it also. Add next. So when all of this is done, if still we couldn't find 2, we return the false. Well, not confident about this. Wrong answer, so we get picked 7, we picked 22. Actually, we need, for 4 nodes, we need 3. Picked. This one, okay, so this, and then this, and then this, and then this. But these actually create a circle here. The last one, the generating circle is wrong. Add edge from 2, we add from key from key 2, we added key 2, from key 2 we get key 2 key from. Add edges seems to work. Ah, oh, God. Issue -1. Yeah. It worked, but why we added, actually there is a circle. Why do we add it? There's still a problem. Even though is generating circle from key from. Ah, I see. Actually, we need to compare for key 2 to join this. So top is key 2. So even if now we don't check the length, it still works. Yes, finally. Great. Okay, but let's do it here for better performance. Hope it works this time. Yay, it works, but it's not fast. The one thing I can think of to improve it is we could actually do insertion sort here. Okay, so rather than we push it, but I need to find index, find the index can I? Oh yeah, we swap it. Yeah. Okay, find the index to insert. Keep swapping. Cool. So this is after I pushed it. So let k equals edges dot length -1, while k is bigger than -1. Okay, no. Let L equals k -1, while L is valid, and edges L, the distance is bigger than the edges K2. We swap them, right? So edges L, edges K equals edges K, edges L. We keep swapping them. We swap them, and oh yeah, I made a mistake. This should be edges dot length -2. The k is bigger than k is valid, and the k is bigger than k plus 1. And we swap k with k plus 1, and k plus 1 equals k minus decrements. Now we could avoid the sorting. Great, I think it should also work. Seems to be something wrong here. After we pushed it, K is the well, K is valid and K is have bigger distance than the previous one. And edges K plus 1, edges K plus 1, edges K. And K decrements. We push it, edges.length now. There's something wrong? This is not fast enough. Yeah, this is actually not fast enough because we don't take advantage of that the array is already sorted. We could use binary search for the index and just do the insertion. But it's still actually there's an index shifting, it's not. But from the result, it's much slower. Okay, I'll keep the edge sort here. Seems not helping here. The other one is that I think we could use this point index to avoid using the strings. Okay, for ij, so actually now it's I and j now. This point index. Now at edge is from 2, so this will be all okay here. From. This 2, 2, 2, 2, 2. From. This is 2. Yeah, it's okay. This is from. This is from. Is from 2. So it's actually working, I think. Yeah, but maybe not improvement. I think my solution actually doesn't work well. It's accepted, but it's fairly slow here. But the basic idea is the same. Kruskal's algorithm. This is the best I can think of. Here, it's obviously quicksort is much better. So okay, so that's all for this one. Hope it helps. Kruskal's algorithm to generate minimum spanning forest or minimum spanning tree. Hope it helps. See you next time. Bye bye.